So here we go. So the session is going to be recorded, so if you want to refer back, I'll try to post it after it loads over the weekend. All right, whiteboard right here. Everyone see the whiteboard, hopefully. All right, so we're talking about the different K values there are, right? Most of the original K values are KC value, right? They're equilibrium constants, where we basically are looking at our, our products, the concentrations of our products. Product 1, right? Product 2. It's really bad B. All divided by the reactants run, right? Reactant 1 divided by reactant 2. Obviously, there could be more or less, and that's the overall just kind of equilibrium constant when we're talking about equilibrium constants. When we start talking about Ka, right? Ka is just the exact same thing. The only difference is now we're talking about our products just happen to be, H3O plus, so an acid, and its conjugate, the conjugate base, right? A minus, all over HA, which is our reactant, right? So we have our products over reactants. It's no different. The only difference is that, in this case, because water is in a different, phase, we ignore water in the equation because it's a liquid and everything's dissolved as an aqueous solution. Then we have you have KW. KW is the same thing, right? The only difference is now we would typically have our hydronium ion times our hydroxide ion. Usually we would have this all over water, right? Because our equation, let me draw the equation in a second. Usually it would look like that because our equation looks like water plus water is in equilibrium with the hydronium ion plus the hydroxide ion, right? But these are both aqueous, and the water is a liquid, so usually it would be water squared. But for the same exact reason, the Kw, the water disappears from the equation, so our Kw is just the hydronium ion. So when we're talking about equilibrium constants, all the equilibrium constants are exactly the same, except for the fact that when one of the substances is in a different phase, we talked about the different phases. If everything's in gas, the gas is the only thing included. If we have gas and liquid, then still only gas is in the equilibrium constant. If a gas and a solid, we still only have gas. If we have a liquid and a solid, then only the liquid. And that goes to the same thing for the Kc, right? If, let's just say, for example, reactant 2 was a solid. If reactant 2 is a solid, then we would eliminate it from the Kc reaction, right? So the equilibrium constant wouldn't take into account. So when you're thinking of all these different Ks, all of the Ks are exactly the same. We just have generically Kc is the overall equilibrium constant, right? Ka is specific to acids. Kw is specific, for water. And then, we've been talking about, which isn't on the exam, right? It's going to be our Kb, right? Our Kb equation, which is just, the same exact thing, but just in regards to bases. And I'm not going to go through that here because it's not going to be on this exam. Does that help you understand it a little, Annie? So don't overcomplicate the thought that it's all the exact same equation. The only difference between all of them is, what are you measuring? They give them different names just because they're when we're looking at KAs, we want to be able to compare KA across an entire group. And what we're really measuring is the amount of acid that's present in solution. So this gives us the ability to compare different KAs so that we can determine which acid is stronger. Did that answer clarify anything about KAs? Let's see, had something else. What about the chart for the relative strengths of acids and bases? Oh, yes. I need to put that in, don't I? Let me write that down. Uh-oh. Although I do have a couple people that you might not need it, which is why I might not have put it in. I don't remember. I'm going to take a look. I'm just taking a note for myself. Let's see, other questions. Percent ionization. You're talking about, Freddie, you were asking about percent ionization. Is that you're talking about on the cheat sheet? Percent ionization shouldn't be that hard, right? It's just the amount of thing that you're looking at for percentage divided by the starting material times 100. Right? It's not, that's what any percent is, right? The substance divided by the beginning all over 100, times 100. You better learn percent by now. If you haven't learned percentage by now, then you're going to be in a lot of trouble.
Dr. Barbosa?
Yep.
What about that sheet that was supposed to compare the strength of acids and bases, that we know, which way the equilibrium is?
So you're talking specifically about, let me see here. Let me find it. Yeah, that's it. Talking about this one here. Not this one here. Wrong one. Let's see if I can find it. This one here. Correct.
Yeah, that's it.
If I forgot to put it in, I have to take a look. So I've had a couple people take the exam, and I don't know if it's a needed one. At least not right now. You might need it on the next exam more so. So I have to take a look. I took a note for myself, and I will look at it and figure out whether or not it's needed or not. And if it is, then I didn't put it in for the other people that took the exam already. I might have to go back and have them redo a couple problems or something. I'll let you know. All right. Let's see what else we have. We've got a whole bunch of comments going on. KP. Oh, yeah. KP is, I see your KP comment there. Let me share the KP. All right, you're looking at KP. Okay, KP is the exact same thing. The only difference is, right, we have our pressures of our, right, product one times our pressure of product two. That's product one. Product two. All divided by our pressures of the reactant 1 times the pressure of reactant 2. And the reason we can do this is if we look, get into chemical equilibrium. Let's see if I can find the slide. There you go. Let me share this other slide here. All right. Okay. It's coming. Come on. All right. The reason we can do this and have the Kp, and we can substitute Kp into this equation and have Kp substitute for Kc, is when we're looking at the individual pressures, go on to the next slide, right? We take the ideal gas law, PV equals nRT. If we rearrange PV equals nRT over to solve for pressure alone, right, we end up in a situation where we have our N over V times RT is equal to the pressure, and we know that N over V is just our concentration, right? N over V is our concentrations. So when we plug in, so let's just go here, right? And we instead rearrange, and if we solve for concentration, right? So if we solve for concentration, which is equal to N over V, this is equal to RT, right? Am I doing this right? No, it's equal to, sorry, P over RT, right? All I did was rearrange the first equation. So I solve for N, the concentration. If I then plug in this into the, I go back here and I plug our concentrations in terms of pressure into the Kc equation. All right, so let me do that. So we have our Kc is equal to our concentration. I'll call this concentration 1, which is just P of product 1 all over RT, right, times P of product 2 all over RT, all divided by the pressure of reactant 1 all over RT, and times the pressure of reactant 2 all over RT. And you can see how when you have an equation like this, all the RTs are eventually going to cancel. So you can rearrange this to solve and essentially set this equal to the pressure equation here, right? Where we've gotten rid of all of the concentrations and basically just use pressures, and that's why we call it the Kp. So it's the exact same equation as Kc. All we did was substitute in for concentrations, and we get pressure out in the end. All right, working my way down through the questions here, and then we have Ka. So Ka is basically an equilibrium constant because acids are in equilibrium. Correct. That's all Ka is. Ka is, Kw is, Kb is, Kp. They're all just normal equilibrium constants. They're all based on the original equilibrium constant shown here. all of them are exactly the same equilibrium constant. All we did was substitute in different reactants and different products, so we gave them different names. And the reason we give them different names is just so we can, group them together so we can compare them. All right, next question. What if it's a strong acid that isn't in equilibrium? If it's not in equilibrium, then there's no equilibrium constant, right? So it's 100% dissociation. So whatever, there's no equilibrium, there's no backwards. So right when we have just a forward arrow, there's no equilibrium arrow. So, whoops. If there's no equilibrium arrow, then there's, essentially there's no K to calculate for.
So you won't make us do any calculations with strong acids or strong bases?
No, you can't. There are no calculations for strong acids or strong bases in regards to, not in regards to equilibrium. You can make the assumption, right? The concentration. So if you have a strong acid, let's just say we have a strong acid HCl, right? And that dissociates to give us H plus Cl minus. We know that if we put in 6.5 a molar concentration of HCl, because this is because the dissociation here is 100%, right? So this dissociation is 100%. I know that I'm going to have 6.5 molar H plus solution out in the end, right? So you can figure that out because it's 100% dissociation, right? So you don't have to use an equilibrium constant. You know, whatever you put in the beginning is what you get out in the end.
And like if the stoichiometry wasn't 1-to-1, then
yes, yes, it is in this case, correct.
Okay, one more question. Sorry. Are you gonna have us memorize the strong acids?
Memorize what? I didn't hear you.
We have to know by heart like which acids are strong and completely dissociate.
No. If there's a question on there, I'm guessing I didn't put a question on there, which is why, it could be because I just was up till 2:30 or 3 in the morning making that exam, so and I just forgot to put it in. But I'm going to take a look at the problems. I don't remember all the problems by heart, so I'm going to take a look at them and see if you needed that table. But I didn't expect you to memorize it now. I mean, there's not many of them. It's just the halogenated acids and sulfuric acid, a couple others. Let's see what else we have. Questions. Page 671. Let's see. That's still the same question. Yeah, that's the table. Okay. Yeah, if you need that, I'll take a look through the problems. See if you need that table or not. Number 7 on chapter 15 for Brian. Let's get it open. All right. Share that window. Number 7. There we go. All right. So this is the question. As shown in table 15.2, Kp for the equilibrium of nitrogen plus 3 hydrogen atoms gives us 2 ammonia molecules is 4.51 times 10 to the minus 5th at 450 degrees Celsius. for each of the mixtures listed here, indicate whether the mixture is at equilibrium at 450 degrees Celsius. If it is not at equilibrium, indicate the direction toward a product or toward reactions in which the mixture must shift to achieve equilibrium. So we're starting off first. We have a 98 atmospheres of ammonia, we have 45 atmospheres of nitrogen, and 55 atmospheres of hydrogen. So when you're working through this problem, right, it says to calculate the reaction quotient in each case and compare it with the Kp, right? So we know our Kp equation, right? It's just our products, the ammonia, right? And this is going to be squared. So you see the little square number there because we have two ammonia atoms, molecules. So it's pressure squared of ammonia divided by the pressure of each of our reactants. We were given that number. So to calculate our reaction quotient, we do the exact same thing. All we're doing is plugging in the data they gave us, right? So 98 squared comes, that's the amount of ammonia we have present. 45 is our nitrogen, and 55 is our hydrogen. So we just simply do the math, and we, go through, and we eventually calculate that we have 1.3 times 10 to the minus 3. And this is because our Q, the reaction quotient, is greater than the the equilibrium pressure constant. The reaction will shift towards the reactants to achieve equilibrium, right? Because what does this mean, right? If this Q is larger than our Kp, right? It's a larger number, right? 10 to the minus 3 is bigger than 10 to the minus 5. That means we have a larger quantity, right? The number on the top, our product, is larger. So to head towards equilibrium, that number has to get smaller. So in order for that to get smaller, we're going to shift towards the left, right? So we have a shift moving towards the left, towards the reactants. The next one, we do the exact same thing, right? So we're just plugging everything in one more time. This time, though, the one difference is since we don't have any hydrogen, we have no hydrogen. And in this case, you're basically heading towards infinity is basically the what the solution is, because if you don't have any hydrogen, then your Q is going to be, again, much greater than the Kp. So in order to achieve equilibrium, you're going to have to shift towards the reactants again, because essentially there must be some hydrogen present to achieve this equilibrium, right? That's the only way you're going to be able to shift. If there's no way to shift if you don't have any hydrogen present. It's impossible to shift to the right, right? So the only way you could shift is to the left. So in order to form hydrogen, you have to have ammonia, decomposed back into hydrogen. And then let's see what else. And then next one. So we have 13 atmospheres of ammonia, 27 of nitrogen, and 82 of hydrogen. So we plug those all in here, and you can see, and I didn't mention it before, but right, this is cubed, right? That's cubed because we have 3 hydrogen atoms up here, right? So we need to make sure that we recognize that this is cubed. The hydrogen is cubed. Let me go back up. So you can see here, we just plug in, we get 1.1 times 10 to the minus 5th. So you have 1.1 times 10 to the minus 5th versus 4.51 times 10 to the minus 5th. And since the Q is only slightly less than the Kp, right, it's a little less than, the reaction is going to shift slightly towards products, right? In this case, Q is less than Kp. All right, so now because of this, because it's smaller, we need to increase the product this time instead of decrease it. So in order to increase the amount of product to make this a larger number, to make it more equal to the Kp given, we have to shift towards the product side. That answer your question? Any other questions on that? Any more questions? Okay. So you got it. Freddie, you say so. Is there something beyond the so? Did I miss anybody's question? If I did, just add it to the bottom. Rate laws. So here's chapter 14. Any particular one for chapter 14 on rate law? You can see I actually covered some of the discussion. This is problem number 2. So if you look at the recording for problem number 2 from the other day. All right. So you're saying first order, second order. All right. So that's the discussion for problem number 2 is basically determining order. You can see all the scribbles here. Right. Let me see if it will let me erase. It won't let me erase. Why won't it let me erase? Let's see. It won't let me erase my comments from the other day. I don't know why. Huh, there we go. I got it. All right, so when we're working through problems to compare orders, Freddie, what you're going to be doing is you have right, your traditional rate law, right? So you have rate of an equation, in particular the rate of this equation is just going to be equal to, right, the k. Let me make that a little k so it doesn't. My eraser's not working. Oh. My Adobe just froze. Give me a second. There we go. Okay. Here we're little k. Rate constant times our concentration of our CH3 Cl to the x power times the concentration of I minus to the y power. Right? We don't know what x and y are yet. Right? So we have no idea what x and y are. So all we're going to do is we're going to, and you can see down below, is you essentially set up the equation so that you can compare rate 1 to rate 2. And your textbook, maybe I should use different numbers, different letters. Not working. Instead of x and y, they use m and n up here, right? M and n. So we'll use m and n. And one of the things you need to look at when we're looking at and we compare the two different rates, we have a table here, and in order to determine rate constants, what you need to do is you need to have two different experiments for each rate you're trying to compare. So if we look at equation 1 and experiment 1 and experiment 2, when we compare experiment 1 to experiment 2, we're changing the concentration and the CHCl3, but we're keeping the concentration of the I minus exactly the same. So what that allows us to do is when we enter into and compare the rates, we have rate 1 divided by rate 2, and we plug in all the data. So you can see, right, the 1.36 and the 2.72 are just the rates that are from the rate table. We then plug in the concentration of each of these substances, right? The 1.5 for our initial CHCl3 and 3.0 for our CHCl3 at the second concentration. And then because we have the same concentrations for each of the iodide in this case, those are going to cancel each other out, right? Since those cancel each other out, the K's are going to cancel out because they are no longer part of the equation. So then we just simply do the math, right? If we take 1.36 times 10 to the minus 4 and divide it by 2.72 times 10 to the minus 4, we end up with the 0.5. Now we do the same thing for 1.5 times 10 to the minus 3 divided by 3.0 times 10 to the minus 3, we get 0.5. So when we compare these two, you can see that if we're trying to figure out what x is, or actually I should say m, keep doing it. My eraser's not working today. Oh well, it's the letter m, right? So m is going to be equal to 1. So we know in this particular instance for 0.5 to equal 0.5, m equals 1. So I'm not going to go through the other half. It's just the same exact thing. You end up with 0.5 and 0.5. When you end up with a first order versus a second order, something that would be second order, when you change the concentration, for example, in this problem, and the concentration doubles, if the concentration doubles, if the rate doubles, when the concentration, let me think about what I'm saying here. If we take, for example, all right, so if we double the concentration, right, so go from 1.5 to 3.0, but instead of going from 1.36, let's just say, let me do the math here. So if this instead went to 5.44 times 10 to the minus 4, right, then this wouldn't be 0.5, right? This would be 1. So it would be 1 is equal to 0.5, right? And you would see that in order for 1 to be equal to 0.5, you would have to hold this up to the second power, right? Let me see, 0.5. No, that's not right. What am I doing wrong? If concentration doubles, I'm making a mistake here. If concentration doubles, let me go to that's what happens when you try to make up data on the fly. Let me go to chapter 14, PowerPoint. Bring up an actual slide. Okay, fine. Here it is. Oh, that's not it. Oh, I know what the problem was. I figured out what the problem was. And this is my own doing. What I should have done and the answer key here, I actually did incorrectly, is I should have had the top one be rate 2 and the bottom one is rate 1. It just happened to work out for this particular problem because they're both equal to 0.5, but that would have instead inverted these numbers, and I apologize ahead of time. So instead it should have had would be 5.44 divided by 1.36, and that would have been equal to the 3.0 times 10 to the minus 3 divided by 1.5 times 10 to the minus 3, which would have instead given us an equation of 4 is equal to 2, and that would be 2 to the m power. And then in this case, m is going to be equal to 2. So learn from my mistakes, and I'm going to have to correct this answer key. So this should be the rate with the higher concentration, rate 2, ends up on top. And then something that's zero order would basically set it up in a situation. And maybe go here. Let me see if they have a 0 order example. They do. Right. And that's what I would have. Let me share this screen here. So you can see the 0 order would have been in a case where you end up with, oops. Let me just move that out of the way. I can't write on it until it's expanded. Right, so the 0 order ends up in a situation when you have 1 equal to a number that where the n, you basically can never make n equal to 1. And they do rate 2 to rate 1 here as well. And I think that's upside down, and that's probably why I did it incorrectly. Numbers make more sense if you invert them. Does that answer your question, Freddie? Where is it? Let's see. Let me see. No, then it would be 0 order. Yeah. Any more questions on this type of problem? All right, Cameron, number 3 on problem 16. Let's see. Problem set 16, number 3. It is identify the Bronsted-Lowry acid, Bronsted-Lowry base, conjugate acid, and conjugate base of each reaction. All right, so for when you're working through these reactions, you have the acid, it's a, the acid-base equation, and you have, whenever you have the acid and the base, so the Bronsted-Lowry acid and the Bronsted-Lowry base are always going to be on the reactant side, right? Whereas the conjugate acid and the conjugate base are always going to be on the product side. So that's the first rule. Always recognize that the acid and the base react together to give you the conjugate acid and the conjugate base. So you don't want to mislabel just by doing that. So when you're looking at the equation, you should have an equation, and you have your equation here, and you want to compare the left to the right. And you can see the Bronsted-Lowry acid is always the thing that gives up the proton. So if you look at it before, you have an extra proton, whereas after, right, you've lost the proton. So your acid here is always going to become a conjugate base. Whereas then you have your water. In this case, the water is a base, and it's the thing that picks up the extra protons. So we went from 2 protons to 3 protons. And that base is always going to become a conjugate acid. So that's how it goes for simple reaction with water. The next example, so you have to pay closer attention to this because this one has 2 different substances, both are negatively charged. So you have to pay attention to where the which one is losing the proton. So it's just simply comparison, right? Whoa. Someone there? All right. So you have the substance here on the left, the HSO4 minus. You compare it to the one on the right, the SO4 minus. You can see that the proton here was lost. Right. So you would label this one as an acid because of the fact that it lost its proton, and then its conjugate base is, right there. And then conversely, the HCO3 minus is the one that gains the extra proton on the right-hand side. So it's the base, and it becomes the conjugate acid. And then for the last example, it's the exact same thing, right? We have, different substances. We compare, look for which one lost the proton. So we go from 3 protons on the hydronium ion to 2 protons in water. So that's labeled as the acid, and the water is the conjugate base. And the HSO3 minus, right? It's the base, and it becomes conjugate acid. That answer your question? Are you going to need to know the difference between definitions of acids and bases? You're talking about like Bronsted-Lowry versus the others. They're all essentially grouped together for the most part. We'll eventually be covering Lewis acids as well, and Lewis acid versus Bronsted-Lowry acid base. They all mean exactly the same thing. The Lewis acid will expand this scope quite a bit more, and you'll probably need to understand the difference of a Lewis acid versus a Bronsted-Lowry acid. But Bronsted-Lowry is pretty much the standard for most of what we do now. Other questions? Anyone? No one wants to keep me around longer? Get all close-up pictures of me. Since a few of you were on it, are there anything you've been online in several other classes in addition to mine? Are there things that seem to be working, some of these other classes that would be helpful to implement? If you can think of anything, let me know. New question.
There is something we do in physics. Can you hear me?
Yep.
Okay, well, in physics, Dr. Lowell just shines his camera down at the whiteboard, and he just draws on a whiteboard instead of doing it on the screen, because it's messing around.
Yes, Dr. Lowell went out and bought a camera, and he's got it hanging from his ceiling. And yeah, I unfortunately don't have a little whiteboard at my house that I could do that with, but I can see some value in that. Yeah, he showed me. I was online with him checking out, and he was showing me with the little camera, his little setup. He actually has 2 separate cameras. He has his computer camera and a separate document camera, and he switches back and forth between the 2. And he's just got it hanging from the wall, pointing down at the whiteboard. And the reason he did it was because of lack of his touchscreen didn't work very well. Unfortunately, well, if I can come up with something, I'll see if I can. But right now I don't have a separate little camera. He loves you more than I do. Probably true. All right, we have another one. It says, when finding the instantaneous rate of the reaction, will you give the tangent line? Yes, I told you I would when we were in class. I would give you that if you needed it. I won't have you figure out tangentials. When do we use the half-life equations? When you're asked to calculate a half-life. That's about, I mean, literally you would be asked to calculate a half-life of a reaction, and that's pretty much why you would use that. Half-lives are extremely important for biochemistry, so you won't see a lot of half-lives. What do you think? There is occasional half-lives discussed in organic chemistry, but very, very few. Half-life is one of those things that when you get into biochemistry will come back and will dominate the conversation, so to speak. There's tons of half-life discussions in biochemistry, because that's how you compare protein to protein. They're typically most discussions about half-life, about how fast a reaction occurs. Let me see if I can look at this here. Switch through the slides here. Oh, there it is. Half-life. There we go. Right. So, I mean, you're only going to be asked half-lives. You would, in order to calculate half-life, right, you'd be working through an equation, and you're literally asked for what is the half-life of the reaction, or you're given a half-life and you're asked for a particular concentration. So you'd just be working back and forth in between these different equations, right? So for first order, you're given a half-life, so you'd have the T half, or you're given a K, right? And you just calculate back and forth. You wouldn't really have, let me just blow the screen up. So right, if you were given a half-life, then you would be asked to calculate what the rate constant was, or if you're given the rate constant, and then you're asked to calculate the T half. And then the other, unless of course it was second order, and then if you were in second order, right, you'd have a second order rate constant, or T1 half, right? And then you can see the second order T1 half is dependent. Right, that's dependent on not only on the rate constant, but also on the initial concentration of A. So you can calculate back and forth. So in this equation, you'd have to be given two things, right? You'd have to be given a rate constant and an initial concentration, whereas, and in order to calculate T half. That's funny. Other questions? Everyone ready for tomorrow? Somewhat. That's not what I want to hear. You need confidence. The answer is yes. Yes, Freddie, you should have an idea. even if it's not on the exam, you should definitely know what factors affect reaction rate. And right, increasing temperature makes it go faster, right? You need to know about let's see. Where are they? Oh, there we go. Right. You have your temperature. You have your frequency of collisions, orientation of molecules, right? When we have, my computer's going slow today, right? But when you're thinking of, increase of temperature, your reaction rate goes up, right? So you should definitely know a little bit about that. You should definitely know about which direction it's going to make it go. It depends on the exothermic versus endothermic reaction, right? Right, here we go. Right, so if you have an exothermic versus an endothermic reaction, let me try to find those. Right, here's the. Where are those questions? There's a bunch of questions in here. Try to get through here. Can't I find those questions? I'm not finding the slides that I'm looking for. I don't think. I think I might have just drawn them in class. If we go to, let me switch. Sorry, everyone. Can everyone hear me again? I disconnected on accident. You will hear me. Maybe someone say yes if you can hear me. Oh. All right. So sorry about that. I was trying to switch screens and I clicked the hang up button instead. Technical difficulties, I guess. Is that what you would call it here? All right. Let me go to the whiteboard here. All right. Oops. Need to do that. All right. So if you have a reaction and you have two different reaction diagrams. Right, so in the first example, right, we have our activation energy. Right, and then we can see in this particular example, our delta E is going to be a positive number, right? It's going to be a positive number. Whereas in the second example, we have our activation energy here, and our delta E here is going to be a negative number. Oops. Let me just put this somewhere on the other side. Our delta E here is going to be a negative number. And let's see something here. All right, so it's still working. All right, so delta E is equal to a negative number. All right, so we have the reaction on the left is going to be our endothermic. reaction. The one on the right is an exothermic reaction. So when we're looking at endothermic versus exothermic, right, in order to have an endothermic reaction occur, we have our reactants, right? And we have to add heat to the reaction in order to drive the reaction to products. Right. Makes sense because our products are higher in energy than our reactants. Whereas on the exothermic side, we have our reactants, and when they move over to products, they're going to give off heat. Right, heat is given off. So if you add heat to the reaction, right, when you add heat to the reaction on the left, because heat is on the left-hand side of the equation, these are supposed to be, I should probably correct these. These are equilibrium arrows. Okay. So when we add heat to the reaction on the left, we're adding, placing a stressor on the left-hand side of the reaction, so that we're going to shift the equation towards the products. Whereas in an exothermic reaction, when we add heat, we're going to shift in the direction of reactants. Right? So does that kind of make sense? Is when you're thinking about these things, always think in reaction diagrams, what's going on. We have exothermic or an endothermic process. And when you have the shift occur, you're going to have a shift that basically it's going to be dependent on whether or not you need to add heat or take heat away. And obviously, the same thing goes whenever you place a stressor or add reactant to the left-hand side, it's going to shift towards the products. Or if you take products away, it's going to shift towards the reactants, right? So that's just, for all the reactions, right? If you add extra reactants, then the product, equation has to shift to the right. Or whenever you add products into the reaction, you're always going to shift to the left. Did that answer everyone's question, or was it Freddie's question? Any other questions? Clarifications? Anyone there? No more questions? Nope. Everyone's getting an A++ tomorrow. I hope. Cheering for you all. All right. 100%. I hope so, Brian. I don't think you students all recognize how much we wish all your students would do 100% all the time. %. That's failure, Annie. You have to vote for more. All right. Well, if no one has any more questions, I think I've delayed long enough. So if no one has any questions, there's probably no more questions. You have one more? I was counting on you, Freddie. I was waiting. I tried delaying. What's the last question? Waiting for it.
He tried talking, but his microphone doesn't work. He said, "What do we need to know about the rate determining steps?"
What do you need to know about the rate determining steps? Good question.
He was like wondering about like if it's the first step is the faster one versus if the second step is the faster one.
Okay. Let me go back here and share this again. All right. So if you have your overall reaction, I'm not even going to draw one out, right? So let's say we have an overall reaction, and then we have step 1 and step 2. Okay. So if step 1 is a fast and step 2 is slow, right? Then as your reaction proceeds, right, the material step 1 will have no effect on the rate because the reaction rapidly proceeds to the second step, which is going to be the slow step. So the rate, when you're looking at the rate of a reaction, right, the rate of the reaction is going to be solely dependent on the second step, right? Whereas if you had it the opposite way around, where the first was slow and the second was fast, then you're going to have the rate is going to be dependent on how fast the material is proceeding in the first step. And if the first one is a slow step and an equilibrium, then you have to take into account the equilibrium, because not only does it form product, then it also, that product can then go in the reverse direction. So let me go to the slides. Let me find the right slide. All right. These are the slides here. So, all right, so we have our steps that affect rate, right? So you can see in the first case where the slow step is in the first step, right? What happens? Let's go through. The initial slow step. Okay, let me go. Trying to find the best step here. Let's go to the problem here. All right. So in this particular example, we have our slow step is the first one, and our fast step is the second one. And neither one of them are in equilibrium, so it doesn't make a difference. We're just simply going to be looking at how this affects, right? In the first case, because the first one is slow, you have a rapid transfer of products moving directly over to so the product that is formed in the first step, in this case, it's going to be the oxygen, is then consumed very rapidly in the second step, right? So the oxygen moves over to the second step and is rapidly consumed. When you add these two, the two reactions together, right, you can see that that's the step here. When you add them together, you end up with the intermediate oxygen is on both sides. We're going to cancel those out. But if we're looking at how this affects the rate, since the rate of this reaction, the second is going to be completely dependent on the first step. The rate of this reaction is going to be solely dependent on the amount of N2O that is in the first step that produces this oxygen intermediate, which then can react in the second step to move another molecule of N2O off the product. So the rate of this reaction, as you can see down here, is going to be solely dependent on the slow step, which just has one N2O molecule present. Right. Even though if we look at our overall equation here, the overall equation has two N2O molecules present as reactants. So our rate is not dependent at all on two N2O, but only one, because only one is present in the rate determining slow step. Let me go to, no, I'll keep that for a second. Let's go here. So then if I go to sample here. Right. Okay. And in this example here, they threw a curveball at you because they have the first one both fast and in equilibrium. And in this case, because of that, you can see that our we have to take into account the concentrations that are occurring in the first step in addition to the second step. Let me just go. All right. Let's just look at the individual reactions right now first, right? So when we have two different equilibria, two different steps. So in the second step, though, which is a slow step, this second step is the one that controls the equilibrium. And since the second step is the one that controls the equilibrium, overall our rate is just going to be dependent on the slow step. So the rate of our reaction is equal to K2 times the concentrations of each of our reactants here. The one problem in this particular step is that our N2O2 is not a reactant, right? So if we look at the overall reaction up at the top of the page, the overall reaction does not contain any N2O2, right? All we're reacting are two nitrogen monoxide molecules with bromine to give us our products. So what we need to do is instead take into account the formation of this N2O2, right? N2O2 is going to be the formation of that N2O2 in the first step, right? Has a rate, right? It's a formation step, and we can see that K minus 1, right, which is the rate that N2O2 is being consumed in the first step, is going in the opposite direction, but it's equal to the reaction between the two NO molecules, right? So those two NO molecules react, and they give us a rate of K1 times the concentration of those two NO molecules squared, right? If we think, let me just, if we were to just simply look at the first reaction alone, right, we would say that the rate of this reaction in the forward direction is equal to K1 times the concentration of NO times the concentration of NO, right? And this is where the K1 down at the bottom times the NO squared came from, right? And we also know that this rate of that first equation is also equal to, right, the K minus 1 times, because it's an equilibrium reaction, times the N2O2 concentration. Right, so then we can set those equal to each other because we know the forward rate and the reverse rate have to be, since they're in equilibrium, we can set them equal to each other. We can then solve for the N2O2 and we'll plug that into the upper equation here. And that's what's done on the next slide. Done on the next slide here, right? We solve for the N2O2 concentration, and then we plug that in, right? If we go right back up here, right, this N2, and you can see that rate is equal to K2, and the BR2 are going to be down here. Right? So the rate equals K2 and the BR2, and all we did was plug in for N2O2. Right? And that gives us the overall. We simplify the K2 times K1 over K minus 1 to give it an overall new rate constant. So the rate constant in this example is dependent on the intermediate, if we go back to the original equation, right? The rate is dependent on both the NO molecules as well as the BR2. So even though this reaction looks like it's a third order overall, and the reason for that is because there's two independent steps, and the first step is in equilibrium, which affects the rate of the second step. Correct, Annie. So Annie's saying basically we need the concentration of the N2O2, which is an intermediate, and we get that from the first step. Correct. Because when we're looking at, since this is a two-step process, right? Step 2 is dependent on how much N2O2 forms. Right? We have to form N2O2, and since step 1 is in equilibrium, the amount of N2O2 that exists is dependent on that equilibrium reaction. Yes. Correct, Kenny. We're substituting N2O2 in terms of the nitrogen monoxide equilibrium constant. Does that answer your question, Freddie? Maybe, hopefully. If not, I can explain it another way. We have more problems. Other questions? I'm waiting for you, Freddie. You've always got good questions, and they come up. Your one problem is you're longer than the 7-second rule. I have to talk a little longer. Any hints for the test? Yes. Make sure you practiced all along the way. And if you're studying last minute, then you're going to be studying a lot tonight. No, Brian, you've been practicing all along. You've been working on problems and asking questions. Just trust yourself. And don't, think about why you're doing the calculations, not just how to do the calculations. What is the purpose of the calculation? What is the equation asking you to do? What are you solving for? You got to think at a whole second level. Don't just think, this is an equation and what numbers do I need to plug in? Think, this is an equation. What is the equation asking me to do? What is it telling me? Freddie's a slow typer. I have faith in you, Brian. Andy's done. Brian's done. Is Freddie done? See the camera in. See you, Freddie.